So that was such a kind introduction. It's been my great honor to be a part of this community. And looking out at so many of you, I am reminded of my first SciPy, which had something much closer to 400 people in it. And it wasn't that long ago, it was like 2013. My topic today won't be on my research. It will actually be on some of the observations I've made as a person who straddles the communities between academia and this open source innovative community. And I agree with Serge, this community is extremely innovative, and where really large, pondering institutions may be slow to change, I've been really impressed at the speed with which this community has changed. So let's get started. This is an olive grove in Greece, a very, very long time ago, around 400 and something BC. A olive grove dedicated to Athena was the site of some very interesting conversations between Plato and his friends. And this place was in a general region north of Athens called Hecademia, and it became the location of the first university, Plato's Academy. Right? And so this is sort of what the very first idea of university looked like. It's sitting, discussing under trees, trying to learn from each other about the truth. And that academy, this is Raphael painted this depiction of the walled version of this academy, so eventually they did build a building in which to laze around shirtlessly arguing. And so, of course, this is our ideal depiction of a university and what the academy might look like. A great deal of frank sharing of thought and pondering of the truth. And now, so if I go to the University of Illinois, which is where I am a professor, and I see what's the mission. The mission is somewhat similar to what it used to be, which was creation of knowledge. And they claim that their mission is to transform lives and serve society by educating, creating knowledge, and putting knowledge to work on a large scale, and with excellence, because everything is and with excellence at a university. Not 100% sure what excellence means, but that's fine. So things are really about the same between the Hecademia and today. A few things have changed, so this is a little bit more what it looks like in a university now. All of you, more or less, probably, except for perhaps Axel over there, have been to a university. And this is more or less what it looks like these days. It's scaling up, there's a lot of pressure, people are learning really actively, but there are these large lecture halls. And something else has changed a little bit. They've started to hire people like me, which is a bit different than Plato's scholarchs. And I'll just tell you a little bit about me. So, fun fact, this is my home country. I am from Texas. I went to this Texas Academy of Math and Science. I got my physics degree from the University of Chicago. Went to graduate school to become a nuclear engineer and to contribute to energy that is carbon-free and safe. I then went to a postdoc at Berkeley and got close to the bleeding edge of what's happening in scientific computing right now, data science, innovation. Berkeley is an amazing place to be. But I did have to leave last year, and I'm pleased to say that I'm at the University of Illinois now, so it's all going really well. But with this kind of pedigree, you can get an academic job, it turns out, even if you do open source. And so, indeed, as Serge was saying, and I should note, Serge also really brings it to any project, so don't let him fool you. He's done a phenomenal job, as has Prabhu, on this conference this year. It's been my pleasure to contribute to SciPy, and I'll talk a little bit about the Hacker Within, which Serge mentioned, as well as software carpentry and data carpentry, and the Journal of Open Source Software. And so these are some of the open source activities that I'm involved in. I'll talk about them, what they are. A lot of them were influenced by my participation in the Berkeley Institute for Data Science, which gave me the opportunity to participate in 2 books. One is Effective Computation in Physics, which we'll be signing this afternoon, and then The Practice of Reproducible Research, which has just come out and is a product of that Berkeley Institute for Data Science. But I'm ultimately a nuclear engineer, so just as a fun exercise, I'll walk you through 2 slides which describe all of nuclear engineering. Maybe 3, maybe I'll give you 3. So this is a little white neutron hitting a nucleus. That nucleus, because the neutron, once absorbed, makes the nucleus unstable, breaks apart into 2 pieces. And there's a little burst, kapow, of heat. And 3 more neutrons come off, 2 or 3, and depending. And that fission reaction can cause other fission reactions, right? Because those 3 other neutrons might hit other uranium atoms, probably, and cause more fissions, and then you get the chain reaction. Right now, everyone understands the nuclear chain reaction. You could all be nuclear engineers tomorrow. The only other piece is understanding how nuclear reactors work. We do all those fissions inside the reactor vessel. We heat up a lot of water, typically, and we move it past other water in a different container to move a steam turbine. And that steam turbine keeps the lights on. 20% of your lights in the United States, and the vast majority of our clean energy, because it doesn't produce any carbon, this process. So this is why I do what I do, is I'm interested in nuclear energy. Interestingly, we are facing a time when we need to move really quickly about the climate and our carbon emissions. I don't know if you guys noticed this, but a piece of Antarctica the size of Delaware, I believe, fell off recently, like last week. It's in the New York Times, and we can't ignore this anymore. We don't have time to wait. So this is my opinion on that, and we'll move on from my science with just one more comment. So nuclear engineering comes from a kind of sadder place. Not all nuclear engineers are focused on energy. The vast, vast majority of them today are. Some, and in fact the originals, were more focused on the development of the atomic bomb. And a great deal of our knowledge as nuclear engineers comes from that work in the Manhattan Project. Here you see Stanislaw Ulam, John von Neumann, and Richard Feynman sitting together in Los Alamos discussing things. And this is how innovation is done, how truth is discovered, and it's a lot like this olive grove, except in the desert in New Mexico. And together, they developed a lot of science that contributes now to the lights that are on. But they also developed some really interesting stuff. So John von Neumann, during this time, had the following quote, "I am thinking about something much more important than bombs. I am thinking about computers." And indeed he was. He and Stanislaw Ulam, who's also sitting there, together developed an algorithm that probably a number of you use despite not being nuclear engineers. How many of you use a Monte Carlo type algorithm in your work? Raise your hands. Yeah. So the Monte Carlo type algorithm was developed specifically for neutron transport. It's very good at modeling this very complex process that we only understand by the probability of various reactions. Okay? And Stanislaw Ulam and John von Neumann developed this algorithm in Los Alamos during the Manhattan Project, and they together then programmed it. It was the first program in a general purpose computer. John von Neumann programmed it into the ENIAC. So little did you know, not only do you now know how nuclear engineering works, but you also know that your ancestry in an algorithmic sense includes some nuclear engineering. Great. So I too try to think about computers. And I also think about education and the way that computers interact with education. So something that I'll maybe talk about for the next 20 minutes or so are the things that I believe that academia is learning from open source. Some of the things that I think open source could be learning from academia and is already learning from academia, and some of the things we need to work on together. So education, I believe, needs to transfer knowledge, communicate some concepts, convey to students how to think, and prepare learners for their futures. But computers have changed everything. It's very different. these days than it used to be. Lorena gave an amazing talk a few years ago here at SciPy exactly about this quest for computational thinking in our curriculum these days. She'll appear again later in my talk. And in this universe in which you have a complex computer presence in education and research, my PhD advisor, Paul Wilson, suggested that all his graduate students should get better at diving deep and finding the hacker within themselves in order to get their work done. And so together we had this group that we called the Hacker Within. And the Hacker Within is really responsible for all of my involvement in SciPy, full stop, because it involved a lot of amazing people, and we decided that Scientific Python was the way to do everything. But it's basically a peer-led organization for sharing scientific computing best practices. We were scientists in graduate school at the University of Wisconsin, and we were using computers, but no one had ever taught us how. And so we got together. It looks kind of like this at UC Berkeley now, at BIDS. This is what a Hacker Within meeting looks like. It's got a couple chapters now around the world, but it's basically a lot of graduate students and postdocs saying, this is how I tricked out my text editor last week. You should try it. So there's an original chapter at the University of Wisconsin. There's now one at BIDS at the University of California, Berkeley. Briefly, there was one at the University of Melbourne, but not anymore. Similarly, Michigan State, so too at Yale. Swinburne University of Technology in Australia actually has a fairly well-sustained version of the Hacker Within. The University of California, Davis had one briefly, but then it seems to have morphed into something slightly different, so we won't count that, but there's also now one at the University of Illinois, which was there before I got there, I should note. Anyway, so we've got a few chapters, but the things that are good, that help to make the Hacker Within work are communities. So, one of the things I think that we learned from open source when we were starting the Hacker Within was this notion of community. And in particular, the kinds of notion of community that you see in open source, a very democratic anarchy, some maximal permissions. As soon as someone starts helping, you start giving them responsibility, right? As soon as someone makes a good pull request, you give them push permissions. This is a very good way to get people to be involved. Charismatic leadership, so I'm not talking about myself. At the University of Wisconsin, we had a phenomenal person called Milad Fatnejad, who makes a lot of jokes, and it's really important to have someone like that leading an organization because people want to be around them. We also shared beer occasionally, and I think we were learning all these things from the kind of camaraderie that you see in open source. And this is what it looked like. You'll recognize a few of these people from the SciPy community. Matt McCormick, Matt Terry, our Anthony Skopats are all in this picture with me. These are the original Hackers Within. So this is how it became the case that I became involved in SciPy, is that we together had this goofy graduate group. It's also fairly peer-driven. It's peer teaching and learning, right? And people pay attention to their peers. They like to hear from people just like them. Interdisciplinary, so we had a limnologist. Anyone know what a limnologist is? Yeah. Someone who studies lakes. This limnologist was hanging out with a bunch of nuclear engineers and civil engineers and chemical engineers and physicists. And he was awesome. And it appeals to the desire to show off to your peers. It's harder to show off to someone you think knows a lot more to you. Anyway, so this is pretty relevant if you're sharing these peer things. So we have a whole bunch of topics. This is really tiny text, but there's a website. We cover a lot of stuff: Matplotlib, Intro to Python, etc. There's some other larger organizations that have learned similar lessons. So the Carpentries, for example, have learned a lot from open source and really have an open source model of teaching and learning. So the vast majority of people in this room have heard of software carpentry. There's also data carpentry and library carpentry. At many times in the last many years, I've been told that we might start a HPC carpentry. So these are foundations that are focused on 2-day workshops that try to teach scientists skills for computing. This is what it looks like in that same room that the Hacker Within was in, but it's a little more orderly. You can see it's not a giant circle, but this is a software carpentry workshop. They're 2 days. Scientists teach scientists. All the instructors are volunteers. and the materials are all open access. Max and Belkin taught the software carpentry workshop that was during the tutorials this week. I actually wasn't able to help because I was worried about this talk, but there are a lot of software carpentry workshops all over the world all the time. So, I mean, this is a non-trivial number of workshops here on this map, and it's driven by a non-trivial number of instructors. So the number of workshops really scales directly with the number of instructors, and that number is growing at all times. Oh, right, that's where the team is, and this is a subset of the pictures that are on the website because they don't all fit on one slide. But they're all volunteers and scientists, and if you want to be one, you can. How many of you in this room are software carpentry instructors? Raise your hands. Right? So they're everywhere. Woo! So this is something that, like, I would say academia is learning from open source, because the vast majority of the people on this page are probably categorizable as academics. Some of them are scientists at labs and stuff too, but generally speaking, this is an open source model for teaching academics to be better with computers. Great, so what else? So the only sustainable solution to this problem, where computers are making everything different about how people learn, is going to have to infuse our traditional curriculum with more computing. And Lorena talked about this a few years ago. I want to share just a couple of the cool tools that I've heard of that I think are amazing, that academia has come up with in response to all the innovation happening in open source. You know, it's clear to a lot of academics that open source is great for collaboration. Example-driven teaching is good for sort of contextual computation, and what I mean by that is if you have an example in a class, a student can tie their learning to the real world. And so if you have a computational example, they can tie their computational learning to the real world as well. And so if you just teach them the theory of computing, they'll never learn it. But if you give them a project, then they're capable of tying that authentically to their real world experience and taking it with them. If it's project focused, then it needs to have incremental assignments. So academics like to use proven pedagogy that's backed by science, and now we can use much more modern tools, and NB Grader is a good example of this. I'll bring it up in a second. So NB Grader is super cool. Jess Hamrick, do you mind just like saying, like standing up or showing? Yay! So this is a super cool tool that I've been just blown away with, that I think is changing the face of what it looks like to teach. And you know, Jess has a lot of awesome projects, and BFlow, I think, was standing room only last year. So pay close attention to what she's up to. But this is one of the things that she's up to. And you can see, if you have a Jupyter notebook full of questions for your students, you can say, you know, what that question is worth, how to grade it, you know, using like a little unit test. And then you can distribute those to the students for them to fill out and answer. So this is awesome because it reduces the amount of grading that academics need to do. And much like open source, academics are lazy. The best academics try to be efficient, just like the best programmers. And this is amazing. Anyway, so this is the kind of thing that open source can do for academia and is already doing. So keep an eye out for these kinds of things. Having auto-graded answers to programming problems solves a huge number of issues around how to manage a really large class or even just a slightly complicated class. There's a new curriculum out there. So the Data Science 8 at the University of California, Berkeley is within their new data science division, or Division of Data Sciences, and they are trying to really press the edge of what's going on in teaching. So you can see from this tweet, which has a slide in it, well, has a picture of a slide in it. So it's a slide with, you guys can tweet this slide in my talk with a tweet of a slide picture. Yeah, anyway, there's a little inception going on in this slide, but they teach with Jupyter notebooks, and they're trying to teach using data frames as the basic data structure within all of their pedagogy. They distribute things on Jupyter Hub, and ideally, all of the workflows are very open source through GitHub. They're allowing some of their students to run There are programs on Kubernetes. I don't know how to pronounce Kubernetes. And they have their own sort of plagiarism detection grading Python project called OKPy. So this is kind of amazing. There's a whole cloud-based workflow around this data science project. I guess this is a way that they're hoping that all of the courses within this data science curriculum will be taught to the undergraduates. So this is amazing. This is really changing that picture of like a lecture hall. It's now looking a lot more like a development environment for students. So keep an eye out for that. And I said I would mention again Lorena Barba. Lots of professors now are teaching with notebooks. So I mentioned notebooks for grading and assignments, but Lorena really nailed down some great ways to teach specific lessons with a notebook. So just to recall her amazing keynote from a few years ago, she has this phenomenal set of notebooks on CFD, and this is how she teaches her students. It's notebook by notebook, concept by concept. And she's not the only one, right? I know when to take a hint, and so I too teach from notebooks. Mine are not quite as pretty, but they have a lot of stuff in them too. And this is how my students receive their lectures. So we walk through a notebook together during class. Many of them do figure out how to run the notebooks on their own in class and try things. Many of them don't, and for that it's actually been really useful to have things like Jupyter Hub and MyBinder. So there's a project called MyBinder that displays runnable notebooks. It just serves them up to the web if you point MyBinder at a GitHub repository, and that allows my students to open it up, believe it or not, on their telephones, which is their preferred computing device in many cases. This has amazed me. Actually, yeah, as a slight aside, I have been blown away at the number of students who really think of their phone as equally useful as their computer, and so they bring it to class and they do the little exercises in their phone, which I don't understand it. I think I have pretty good vision, but I must be getting a little old because I could not possibly do that at that size. But they do, and they're able to because of things like these browser-served IPython notebooks that are interactive, like from Jupyter Hub or MyBinder. It's amazing. Right, so we do lots of cool stuff with that. This is what it looks like in nuclear engineering. Ooh, that's a pebble bed reactor. All right. There's also really cool things that are being now sort of produced in the open for course management. So how many of you are professors? Right, keep your hand up if you love your course management system like Blackboard or whatever. Yeah. So yeah, if you've ever tried to customize the system with which you assign assignments and track your students and input your grades and share materials and stuff, these are course management systems. They're often called like Blackboard or Canvas or Compass or whatever. There are a couple of projects just at the University of Illinois trying to create more customizable open source options for this kind of teaching in academia. One of them is called PrairieLearn. So Professor Matt West has created this cool tool that allows you to sync your course content between the student and the instructor, and you have all of your course information in a Git repo. And that then goes up to the PrairieLearn server and it gets served as a course management system. And if you want to tweak the way your course management system works, a lot of it's in Python, so that's awesome. Interestingly, not far from him on campus at the University of Illinois is Andreas Klockner, who also has a course management system that is also open source and also depends on a GitHub repository that holds all your class material. It's called Relate. It may be a little more approachable for some instructors because it, instead of using JavaScript and JSON as the metadata, it uses YAML and Markdown, which some of you may be more comfortable with. They're extremely similar. I mean, don't let them hear me. They probably don't want to hear that, but they do get along very well, I think, and it seems to be useful in different contexts for each. So we are learning a great deal in academia about how to be better at teaching, and we're learning a lot of those things from open source. In academia, however, many people might describe the current research R1 university as teaching as an excuse to do research. I wouldn't describe it this way, but a lot of professors have a great deal of pressure to spend most of their time, and in fact, most of our job descriptions are to spend most of our time doing research. And it is extremely important to the discovery and creation of knowledge that's core and central to the mission of the university. And something we're learning from open source is how to be more transparent and reproducible. Right? This is no surprise to this room. The reproducibility crisis is an enormous problem. Lots of scientific studies are difficult to reproduce, even if they were computational, which should be so easy. It should be very easy to reproduce computational results, but it's less easy than you might think. So this is a great quote by Donahoe. The scientific method's central motivation is the ubiquity of error. You have to assume that just error is rampant everywhere, accidental, intentional. They're just mistakes and self-delusion can creep back in everywhere, and the scientist's effort should primarily be rooted in primarily expended in recognizing and rooting out that error. So what have we done? So I'll talk about a little bit one thing that we've started to learn. So I was excited to be involved in a book project called The Practice of Reproducible Research at BIDS, the Berkeley Institute for Data Science. If you guys are interested in what it looks like on the ground, trying to be a scientist that does the right thing and tries to be reproducible, this book is full of case studies written by scientists who try to be reproducible, what their pain points were, what their lessons learned were, and what their recommendations for other reproducible-minded scientists are. This book was a really fun experience for me. Not only did I write one case study, but I also had the pleasure of writing the lessons learned chapter, where I got to read all of the case studies and synthesize them into some main ideas. And so, reading brings us unknown friends, let us say. I was surprised at the emotion brought forth in these case studies. There's a great deal of fraught scientists hoping that their research results will be reproducible, but finding that things are very frustrating. And it's nice to know that there are others out there with this challenge. So this project was led by the Berkeley Institute for Data Science. The editors were Justin Kitzes, Fatma Imamoglu, also now known as Fatma Denise, I just realized looking at this slide, Daniel Turek, Ben Marwick. There was a bunch of chapter authors and case study authors, and the reproducibility working group. So the reproducibility working group at BIDS is specifically for investigating these questions, like how reproducible is science these days and what could we be doing to change it. And what we did is we basically had a lot of scientists sit down and write workflows of what exactly happens to their data. So it starts somewhere, and then it ends up as a conclusion. What happens in between? And so this is an example. And we sort of decided that for most scientists, there's a sort of stage 1 data input, some stage 2 data processing, and a stage 3 of data analysis. But they looked very different. When you ask different scientists to write down their workflow, you get very different levels. So this was mine, right? Completely different than this other one. I guess I'm more vertical. So generally speaking, you have this raw data, you have a lot of data cleanup and processing that happens. You may have some data analysis or simulation. And we had a workshop where we collected all these. It was 3 days. It was invitation only. We selected scientists that we thought were trying really hard to be reproducible. We didn't select all of the ones we knew of, but we tried. And we tried to do some case study writing and self-assessment. And they all created these various workflows. You can see there's just a broad variety of what comes out of these systems. And each of them was asked to describe their incentives. Why do you want to be reproducible? The pain points. What was hard about being reproducible? Some of their recommendations, and just a little bit of data I tried to collect about the broader group of them. And I'll talk a little bit about what we now need. So the incentives that they reported, this is all in my lessons learned chapter, is they wanted to be reproducible because it allowed them to verify their own work, it allowed them to collaborate with their friends, allowed them to be efficient, and it allowed them to extend their own work. It also allowed a few more fuzzy good feelings. So it allowed a lot of scientists to focus on the science. If you automate all the stuff that's boring, you get reproducibility out of it anyway, right? And then you also don't have to do the boring stuff anymore. you can focus on the science. And a lot of scientists really value that. Similarly, forced planning, scientists maybe aren't super great at self-direction sometimes. Many of them are, some maybe not so much. And so it forced them to plan, and it gave them a safe place for evolution. So anytime you've broken off an experimental branch of a repository, you know that you're safe in that branch to do whatever you want, to break the code, and you can throw it away tomorrow. And I think that was a real revelation for a lot of scientists who had been keeping golden copies of a spreadsheet for many years. Some of the pain points were people and skills. As with all things, people are difficult, and working together is even more difficult. And it becomes like really, really challenging if the people that are involved in your collaboration have a different set of skills. They don't even have to have one higher set of skills and one lower set of skills. Just a difference in skills, a difference in favorite stack can make or break a collaboration. So dependencies, build systems, and packaging were the major headaches in actually getting reproducibility to work. Hardware access is a main constraint for a lot of people. For some people, you need a specific fMRI type machine or a large cluster of CPUs. Testing was hard for people. Incentivizing themselves to test their code was difficult in the time crunch that is academia. So that's not a surprise. And then getting things published with people in a collaborative fashion was a little hard. We'll talk about why that is. And data versioning was hard. There doesn't seem to be, from the academic perspective, a comfortable solution to data versioning. Now there's the Get Large file system and all these things that industry is happily using, but it hasn't really made it all the way through to academia yet in the large scale. And generally speaking, academics don't really have a lot of time, and we have perverse incentives pressured on us to produce. Don't worry about getting it right, like in the perfect sense. Also, some of us have data restrictions for like either biology or nuclear engineering. Things are either maybe export controlled or human subjects controlled and stuff, so that was problematic. A lot of them recommended all of the things that any of you in this room would recommend. Version control your code, open your data, automate everything, etc. Right? These are the lessons that we're really learning in academia from open source. Other recommendations? Avoiding excessive dependencies, or at least trying to package their installation, hosting code on GitHub, and getting DOIs for data and code were really top. Finally, like people really want plain text instead of some kind of funky data set, and they need to set their seeds for random number generation. One more thing. Workflow frameworks can be overkill, so a number of these scientists had tried, optimistically, various workflow frameworks. So a workflow framework is one of these things where someone says, oh, you can just cram your scientists into this one spot in my giant Python framework, and we'll give you all the plots you could possibly need. And that actually is almost always overkill for scientists in this set of 30 case studies. All the ones that tried it, no one tried a single workflow management system, but a number of them tried a few that are popular in the astrophysics community and found them overbearing. So this is an interesting conclusion. What else did I want to say? Oh, there were some outliers. Here's a quote. In our estimation, if someone was to try to reproduce our research, it would be more natural for them to write their own scripts. It has the additional benefit that they might not fall into any of the bugs we may have introduced. Which is that comes from a place of deep honesty. So that's great, yeah. Similarly, this was an important recommendation that I think we forget about in the context of reproducibility. Maybe not all research results need to be reproduced. Scientific funding and the number of scientists available to do the work is finite. Maybe not every scientific result can or should be reproduced. What do they mean by that? And after kind of tossing this back and forth in my mind, I think I've decided this person can be right if what you really mean is the prototyping stage of discovery. When you just try something out, you don't have to write a ton of unit tests to determine whether this quick model is going to work. You try a bunch of models, and then you've got one or two, and then you start writing a real piece of code and real tests and real analysis. And so I can feel that. There were lots of popular tools. GitHub, Python, LaTeX, and R were the most popular among our case studies. Python was the most popular language, quickly followed by R. There were a lot of ecologists in the case study group. But something I thought that was really interesting in my analysis of all of the case studies was that there was a real distinct difference between the R community and the Python community. And this is not to bash R, but I thought it was really interesting. The existence of many Python unit testing frameworks, perhaps too many, meant that most of the people using Python, or not most, about half of the people using Python had tests. The vast majority of people using R had no tests. So these were people trying to be reproducible, people aware of the existence of tests. But because the R framework really doesn't have a huge variety of options for unit testing, it's a little harder for them. And so that's something our ecosystem should be very proud of. Okay. Something else on reproducibility. This is a great Feynman quote. The first principle of science, that is that you must not fool yourself, and you are the easiest person to fool. And so something that academics have been learning from open source is to hold themselves to some strict open guidelines and to make some oaths and pledges toward their behavior. And there's a whole fleet of these open science pledges out there. I think openscience.org or something has a whole list of open science pledges. Many people in the room have written open science pledges. They're definitely worth looking at. They're sort of the kind of thing you might say aloud in public and sign your name to say, I am going to try really hard to be open with my science. And this is something that academics are starting to value and work toward. And I had the thrilling opportunity to go to this super cool castle in Germany recently to join in the creation of one of these pledge lists. And it was this manifesto from this perspectives workshop. You can find it at this link. But basically, it was this cool group of people, some of whom you know. You get together and you write what you think everyone should agree to do. And the general thesis of ours was that we were talking about what kinds of things academics should promise to do when they're engineering open academic software. And some of the things that motivated us were the kind of sad stories. So maybe this is a sad story, maybe this is a boon to us, but Wes McKinney dropped his PhD because he didn't believe that academia could value software contributions. And so that's one of the real problems. I mean, we're all very happy that he did and wrote pandas, right? But some of the things that we said we would do to help with that is be better about citation, right? I will make explicit how to write any of my software. I will cite the software I use to produce my results. When reviewing, I will encourage others to cite the software that they have used. Will Stein said he couldn't figure out how to create the SageMath open source project as a sustainable project in academia, and so in 2016 he left academia. He felt the money wasn't there, the mathematical community didn't care. And so this kind of gets to careers, recognizing software contributions in both hiring and promotion. In the interest of time, I will maybe just show you one more of this kind of long list of these. So when you have a new idea, so this is Elizabeth Siever tweeted this the other day. When you have a new idea in academia, some academics may feel, I hope no one scoops me, but in open science, people think, thank goodness, someone already thought of this, right? And we would like to really embody that more open science attitude towards sharing and collaboration and contribution and extension of other people's work. And so we had this whole section on the development of and use of software. And some of those pledges were I will start as open source. My software will be born open source if possible. I will contribute to sustaining the software that I rely on. So this is a really key one. It requires actual human effort, not just a bunch of motherhood and apple pie. I will contribute to sustaining the software I use and rely on. It's a big deal. I'll match these software practices to the actual needs and resources of the project. So, for example, don't write a whole suite of unit tests for something that just sends out an email or something like that. I will help researchers improve the quality of their software without passing judgment. So I think this is a really important one, and I think we've learned that directly from open source, actually, and some of the difficulties that people have had in open source communities getting started. So I will publish the intellectual contributions of my research, and I will document, package, and release and archive versions of my software. So it's pretty straightforward. One more final thing before it's time for me to stop talking. Actually, I'll say two more things. So one thing is I've been super lucky to be involved this last year in an amazing project called the Journal of Open Source Software. So commit this to your mind. It is a phenomenal location for you to publish your software and get a review of your software by your peers on GitHub, and get a DOI for your software that has been reviewed and is in a journal. Editors include the great Lorena Barba, Kyle Niemeyer. Our editor-in-chief is Arfin Smith. Here I have a whole picture of all of them, but it takes a really long time. Oh, here's the website. This is what it looks like when you commit them. We just recently created a paper describing that process over the course of the first year. And, oh, I thought I had a picture of all of you. There it is. These are our editors. So Arvin Smith is the editor-in-chief, and then a bunch of familiar faces are the other subject editors. So this is an amazing development. It is absolutely at the intersection between academia and open source, and Kyle will be giving a talk on Thursday, Kyle Niemeyer. I'm sorry, Kyle, I forgot how to pronounce your last name. On Thursday about JAS, so you can learn all about it. I was going to ask you guys what you think the challenges are in open source, but I'm out of time, so I'm just going to say I think that SciPy has a little bit of an intersectionality challenge still. I see a lot more diverse faces than I've ever seen. That is absolutely the work of the extremely active diversity committee this year. I mean, it's really mind-blowing, but I think we and academia also have a lot of work to do. So I think you can think of intersectionality as this problem where an underrepresented group, when they're underrepresented in two ways, has a compounded identity issue. So there's women who do science, like Marie Curie. There are women who do Python, like Lynn Root. There are people who do science in Python but aren't women, like Fernanda Perez. And then there are people who do all three, like Lorena, right? And intersectionality is this idea that you're not just a unicorn and therefore out of place, but you're also a rainbow unicorn. So even among unicorns, you're somewhat out of place. And it's compounded. You're like quite weird in all situations. This whole thing actually is typically used in the context of real underrepresented minorities that have multiple underrepresented minorityisms in them. But you can use rainbow and unicorn to cartoonify the problem. And I think that scientific Python resides in this technological space where we have this problem, and the existence of, for example, women or underrepresented minorities in science is low, but so too women and underrepresented minorities in computing is low. So you have this compounding problem. And so my suggestion to you all that I think you can learn from academia actually is to cast a wide net. When we're faced with diversity problems in our undergraduate populations, we go out and recruit from as many schools as possible. We try to bring lots of people in. Claude Steele, another academic, is a sociologist who recognized the importance of stereotype threat in all of this. Lower the barrier, but not the standards, is his thesis on this. Don't tell people we've lowered the standards so you can get in. Just make it easier for everyone to join, and everyone will eventually. This quote is actually really good. It emphasizes that we hold high standards and we believe that you can meet them. And this should be the message to all of the new users that might someday become developers. My easy suggestions for this, I've shared with this community before, but I think all of your projects should have instructions for new developers, comprehensive documentation, a list host, expectations for what a pull request should look like. All the low-hanging fruit in your issues should be tagged, low-hanging fruit. This is a beginner issue. Like, this should be required in all of your projects because that makes it really easy to point to a single link of the issues where a beginner could contribute. And give permissions generously and make sure that your issues are assigned to the people actually working on them. Because if they aren't assigned to the people actually working on them, a beginner might start to work on them and then it gets closed by someone else. And that's really disappointing for them, actually. So targeted sprints are much harder. Appointing an ambassador to new users is a great idea, but really hard. Mentoring users directly on an individual mentor-to-student relationship is really hard, but worth it. And you might consider having users conferences. And you can learn all this from academia. Why? Because graduate school is like apprenticeship, which is like mentorship, and it's been working for thousands of years. This is my advisor and I. He's very proud. I'm clearly really pumped in this picture. An apprenticeship is basically active, social, authentic mentorship. One more thing before I leave you. There's a survey. Academics are still trying to help you be better. And Nell Veracqua, Chris Holgraf, and Stuart Geiger have a survey that you can click on here. I've tweeted the link to my talk. You can click on the link from the slides about how new users and stuff. I don't really know how to describe it, but it's about FOSS interactions with the community, so free and open source project interactions with the community. And that's it. I have a bunch of people to thank. You're all on this slide. Thank you.